order, and then we'll go ahead and get started with those concepts. And let's see. Sorry?
Can you do the last homework first?
The last homework. Sure. All right, so the last homework is divide. All right, so we'll go ahead and get this one done first. Deleted the file name a little too many, too much. Go do folder, save. All right. So I'm going to do this homework, pretty much the same way, using the same logic, as in the C code. Are there any particular question about this homework? I mean, anything specific? Okay, so this is the source code in C, which means with some massaging and including a main program and finishing some of the other stuff, you can actually turn it into a program that runs in C. But I'm not going to do that today. I will just go ahead and finish this program. The first part is, with all the variable definition, they all have to go to the .data section, because otherwise there's no way to change them as you execute the program. So now we have dividend .int, 2000, whatever. This part does not really matter, because my script will inject new values into these particular variables. So we have divisor .int 33, quotient .int 0, and then we have remainder colon .int 0. Okay. So once this is all done, we can switch back into our text section, which is for instructions, and use our usual beginning. This part here is not entirely necessary, so I was kind of skip over that part, because the assignment statements, they're all happening before L1. L1 is where my script will put a breakpoint, and that's exactly where I would inject new values into the dividend and the divisors to test your code. So as far as I'm concerned, at this point it's not really important for me to do anything here, so I will skip over that. L1 is just L1 because this label and L2, they must be defined at exactly those places as far as your code is concerned, because I will stop at L2 to look at quotient and remainder to make sure that those values are correct. So now we can move on to this particular, or the loop logic. Now when you implement the loop logic, you will turn it into the reverse condition, which means you're looking for dividend being less than divisor, and that's a good reason to go to L2. Whoops, loop exit, not L2. So we want to exit the loop whenever dividend is less than divisor. And then you have to put the loop exit here, which is immediately after the loop, but before remainder gets dividend. And then as a while loop, at the end of the actions, we also have to remember to jump all the way back to the beginning of the loop. So in this case, I'll use a loop begin, which in this case turns out to be the same as L1, but it's okay to use two labels for the same location, it doesn't matter. Are we doing okay so far with this code? So I'm just kind of step by step, breaking down the high level logic into lower level logic. Yep.
Could you have just used jump to L1, or would that mess up your script?
I could jump to L1 as well, that's fine. But because L1 is my quote unquote global label, where I would set a breakpoint, I just use loop begin as a separate one, just in case L1 needs to be somewhere else. All right, so getting back to here, I think this is almost ready. Okay, in other words, I can see that I need a compare long instruction, comparing something to something, and then jump, using a conditional statement to loop exit. So it's time to look at this and try to figure out what I'm comparing. the operands of the compare instruction should be the reverse of what is in the C code. So that means that this has to be divisor because it is being subtracted from the other one, from the second operand. The second operand is dividend, and I know that you can only have one single memory operand for each instruction, but I'm writing it this way first, just so that I capture the logic of the code, and then I can fix it later on, okay? Okay, I want these two lines, okay, let me turn on my numbers. I want line 23 and line 24 to basically say the same thing as line 22 as a C statement. So I want to say, jump to loop exit if and only if dividend is less than divisor. So the relationship we're looking for is less than, okay? But I also have to look at the type of the variables. Now the type of the variables is uint32, which means they are unsigned integers. And the L, L stands for less than for signed comparison. So what we are looking for is actually below or C, either one would work because they actually mean the same thing. So you have to use JC or JB depending on how you look at it. JB looks better because it means jump if below. Okay. Are there any questions here about the loop itself? Now, right at this point, I can actually test my code already. What I do need to do is to make sure that the dividend is less than the divisor to begin with, and make sure that this is not an infinite loop.
Does you have to put it in the register first?
Sorry?
Oh, you have to put it in the register
Oh,
first?
yeah, when it assembles, it will complain. The assembler will complain about this. So it's impossible not to fix this one before the program will run.
Okay.
Okay, so yes, I do have to move one of them into a register first. If you look ahead of time, you can see that there's a subtraction all the way down here, which means you have to move divisor into a register so that we can save that move later on. So that's what I'll do, is to move divisor into EAX. It doesn't matter which register.
You can do it the other way around too. I think you can do it the other way around too.
Move dividend into EAX.
Yeah,
I could do that, but that means at the end I will have to, I cannot keep track of dividend in memory anymore. It will be in the register all the time. This way I can keep dividend in memory all the time.
Okay.
But they're equivalent. I mean,
Yeah.
you can do it either way. Okay. So now I can actually test the program. So let me just kind of go ahead and do it this way. Exit. Assemble the program just to make sure I don't make any stupid syntax error like this. Line 29. Ready. Oh, okay. Link the program, and just GDB the program. Put a breakpoint on line L1. Run the program. And now I have to do something before this program will do what it's supposed to, because I have to put something into divisor so that the divisor is bigger than the dividend to begin with. So to do this, if you have looked into the help of GDB, it's the set command that is helpful in this case. So you have to set, and set has many versions. Set variable. Okay, so say set. So just say help set variable, and that kind of explains how to use this one. So you just say set dividend equals to a number that is smaller than the divisor. I think the divisor was what, 33. So we can make dividend 30. That should do it. Actually, this is the same as set variable, so you can say set variable dividend equals to 30. It doesn't hurt to double check just to make sure. So we can use print dividend to test it. You can also use the X command, by the way. You can say X/W for a full word 32-bit, and we want to display this as an unsigned decimal number, which is U, and then do an ampersand dividend. And that shows that it is 30 as well. So I just triple check, to make sure that dividend is in fact changed. So now I'm ready to single step through the program, compare, and right before it does the JB, I can also look at E flags. to see whether the carry flag is already set, because it should be set at this point, and sure enough, the carry flag is already set. Single step, it is now exiting the program. Now it's complaining because I didn't quite finish the entire program. There's no exit code at this point with this program, and that's why it's going to some la-la land. It doesn't know what the instruction is. It's not specified. Okay, but the program does behave correctly, because if the logic is incorrect, it should be in an infinite loop now, because the JC or the JB did not happen, and then the next instruction is an unconditional branch back to L1, which starts the whole thing again. So do we have any questions at this point about this program or how I'm testing the program, even though I'm not quite done with it? Okay. If there are no questions, I'll quit this program and continue with the source code. So now we can just continue with the inside of this particular subroutine. For this particular program, adding 1 to quotient is just add $1 to quotient, and subtracting divisor from dividend. It would have taken me 2 instructions if I did not know that the divisor is already in EAX. But since I know it is already in EAX, I can say subtract EAX from dividend and store the result in dividend, and that basically is the whole thing. So by the time I exit, I also have to implement the next instruction, which is just to move the dividend into remainder. And in this case, I need to put it into a register first and then put it into remainder. And I can see the advantage of putting dividend itself into a register, because it will have saved this time also of not having to use the extra move. So in this case, I do need the extra move of moving dividend into EAX first, and then move EAX into remainder. And then here's L2. Now I just need to supply the exit 0 code. And there we go. All right, so reassemble, relink, and re-GDB the program. I'll just put a breakpoint on L2 this time, and then run the program. Now it's at L2, so I would go print unsigned remainder, and also quotient, and I believe those are correct. Are there any questions? So when you are testing the program, you have to give it some tricky test cases, like what if the dividend and the divisor are exactly the same to begin with? Then the quotient should be 1 and the remainder should be 0. What if the dividend is smaller than the divisor to begin with? Then the quotient should be 0, the remainder should be the same as the dividend to begin with. So you have to test those boundary cases. Now because I'm using uint, so you also have to use boundary cases where the bit pattern could have been interpreted as signed. So you have to use 8 followed by 7 zeros as a test value, because that's the you have to make sure your program does not use the wrong conditional branch instruction and do a signed comparison instead of an unsigned comparison. All right, are there any questions? So the way this is going to be graded is I will give it multiple test cases, starting with the default one, because I think everybody should be able to get this one working. Then I will try to throw the boundary cases, and then the signed versus the unsigned one. So even if you use the wrong flag to branch out of the loop, you will still get partial credit, because you will still be successful as long as the dividend and the quotient, the dividend and the divisor stay within from 0 to 7 and then 7 Fs. So that means even if you make a mistake, your program will still be able to get partial credit. Are there any questions about this particular program, the structure of the program, and how I wrote the program, how I approached the programming part of this? Is that kind of how you guys did it too, kind of like step by step? Or you guys are faster, much faster, you just look at the C code and go like, I can do it in assembly, get it all done. Some people can do it. I used to be able to do it. And then I found out that sometimes I would introduce more bugs and difficult to find out what those bugs are. So these days I just take baby steps. All right, so that's the solution of the divide homework assignment. And your new homework assignment, let me show you a new homework assignment first, just so that in case you have any questions, we can talk about it a little bit first. So your new homework assignment is in topic 6, and it is called File IO. Okay, that's the name of the project. Has almost the same format as the other one. So we'll go ahead and save this file. And I'll just open it in place because I'm not going to do any editing. So opening it here is fine. There we go. So that's that is the code that you have to implement for this particular program. It's really quite simple. The entire thing is one loop, and then inside the loop we have we have basically 2 conditional statements depending on how you count it. This program does only one thing. If it reads as lowercase letter, it will divert it to standard out. If it reads an uppercase letter, it will divert it. It will divert it to standard err. Okay, so it will basically just pipe it to different files. Does anyone or does everybody in this class know how to do the redirection so that you can actually redirect certain things to standard err and other things to standard out, and be able to capture it so that you know what is going into which file? No? Okay, let's go over that first. And in fact, what I'll do is I'll change the instruction to include that so that we know how to test and debug the program. Okay, to debug this program, you need to know how to redirect the output to standard err and standard out. Okay, so let's go ahead and write this very simple program in C first, and then we'll use this C program to help us understand how to do the redirection. So we'll just go ahead and write, I'll just call it reader for redirect. stdio is okay. Just the first line, including standard IO, would probably make a Professor Fox, go like, Okay, so I think it is dprintf, using the file descriptor. So we're printing 1 to standard out like this. So this stuff goes to std out, and then we'll have another one to go to standard err. And then we have our usual return 0 at the end of main. Okay, so gcc-o reader.c. And if you just run the program reader./reader, it will appear that it's printing both of these to the console, and that's because both standard out and standard err are by default mapped to the console, and that's why they both appear in that sequence. So you have to kind of figure out how to redirect these to different files so they can tell which one is being sent to standard out and which one is being sent to standard err. The syntax to do that is to run the program, and then you can use this redirect to specify redirecting to standard out. Okay, so this is basically reader. I'm using this file name reader.std out, so I can remember which file is capturing standard out and which file is capturing standard err. And then the other one, if I remember correctly, is 2 greater than, or 1 greater than, 2 greater than, sorry, 2 greater than reader.std-err. So now I should have 3 files created, 2 files created. One is standard out and one is standard err. We can look at the first one, std out. It should only have the first sentence. Okay, this stuff should go to standard out, and then if I look at standard err, and then capture the other one. So are there any questions about how to redirect the output?
Can you jump back to the program syntax?
Absolutely. Okay, dprintf is just file descriptor print, so you can select which file descriptor you want to use. The first one is basically saying cout less than, and then the string, and then the second one is less than the string. So functionally speaking, you can turn this into a C++ program if you want. Any questions about this particular program? And I think file descriptor 3 is standard aux. So that there's actually a file handle for that too. All right. So when you debug this program, you cannot just run it on the command line because it won't really show you what is going to one file and what is going to the other file. You will have to use the syntax that I showed a little bit earlier, which is use the greater than to redirect to a file to capture standard out, and to greater than to capture the output from that is sent to standard err. So what I'll do is I'm going to put an instruction here, even though I know the video is being recorded, but I want to put this into the description as well. So to develop this program if you're in GDB, and even though for this particular program there is side effect, so you can potentially debug this entire program without using GDB because you can actually observe the output of the program. I would still use GDB, okay, just because it's a much better tool for debugging the logic of your program, and the overhead of running GDB is minimal. Okay, use the following line to perform the redirection. So run is R, less than to specify the input into the program. So you will have to create this test input, okay? So you have to say test.in is something that you create with uppercase and lowercase letters, and some other letters too, to make sure that only uppercase and lowercase letters will be sent to the output. And then the output would be test.standardout to greater than test.standard err. This way, standard in comes from test.in. std out goes to test.standardout, and standard err goes to test.std err. All right? Are there any questions about this particular instruction? If you're not inside GDB, if you're just running the program, then you just say /file IO and then use the same syntax. Okay, the key is you do have to create test.in as the input, test input file, and then the rest is output. Are there any questions about the instructions? No instructions. All right. So let me make sure that we save this first. That's your new homework assignment. You have 1 week to work on this homework assignment. I don't think it will take that long because you can borrow a lot of the code from my program from the previous class. That one actually contains basically the skeleton of this particular program. So all you really have to do is to implement the conditional statements. All right. Any other questions? No questions about the homework assignment? Okay. Now let's go back into the discussion of the stack, because we are already talking about the stack, and we need to go over this stuff here. Okay, so this is the discussion of the stack, and I think we might have covered everything already. Did we go over how to do the push and pop without using the push and pop instructions? I think we did that. Yep. And that's it. That's pretty much all to it, when it comes to the push and the pop instructions. Are there any questions about push and pop before we move on to call and return? No questions? So push and pop are okay? All right. I'm going to close this one and move on to calling and returning. Calling and returning is basically how we do subroutine calls or function calls in C. And it's basically the same thing as in a C subroutine. In assembly, a subroutine has an entry point, which is usually starts with a particular label. It has a single exit point where your subroutine reaches the end, and it has to exit or it returns to wherever it came from or whoever called it, and a body, which is basically the code of the subroutine. So subroutines in assembly language are similar to subroutines in high-level language, but the assembly programming language makes subroutines much more flexible. In other words, you can have multiple entry points. You can have subroutines that are based off of the same base code, but since they use different entry points, they can do different things. Okay? You can also have multiple exit points in a subroutine, but in C you can do that already in regular C code of having multiple return statements within the same subroutine. That actually it's up for debate whether it is a good practice to have multiple return statements inside the same function in C or C++. What do you guys think?
Fine with it.
Hmm?
Fine with it.
You're fine with it? But then it is really no different from having breaks or go-tos or continues.
No, not in my opinion.
Not in your
If you're not
opinion.
jumping around, you're just leaving.
You're just leaving. That is correct. But if you leave, you can impact the code. You can potentially impact some code. Whereas by introducing a return statement somewhere within your program, you can render some of the other code within the same subroutine unreachable.
Yes, sure. But you can do that with a mistyped conditional statement too.
Correct.
So I guess I don't see what extra bits using it really cuts off. You could shoot your own foot either way.
Right.
And
Yeah.
it
To
doesn't
me,
really give you a new gun to do it with.
it depends on how you want to analyze your program.
Yeah.
Okay. The only time I would do that, having multiple return points, is when I do recursion.
That's generally when I do it.
Right. But if you're not doing recursion, it is generally speaking a bad idea to have multiple points in your subroutine that can return. But in assembly, you're definitely free to do whatever you want to do. All right. So let's move on to the next slide. Is everybody in this class comfortable with functions in C? I sure hope so. Okay, so we have the conceptual behavior of calling and returning. Basically, call is the invocation of a subroutine, and read is the returning from a subroutine. That's basically it. So what we can do right now is to write a very simple subroutine to illustrate this point here. So we'll go ahead and write a particular program just to illustrate this point. Okay, so this is the entry point of your entire program. I will first have a call here to call a subroutine. I'll just call it function 1. And here we have some no-op instruction and then the exit code for the entire program. There we go. And in assembly programming, you can put your function or the subroutine that you're calling anywhere you want. Okay, you can put it before the start, you can put it after the start. It's just that you don't want it to be interleaving, some other subroutines. So function 1, doesn't have to do anything fancy. I'll just put some no-op instruction here so it is obvious that we're in function 1, and that's my entire program. Okay. So at this point, let's not worry too much about. Yep, go ahead.
Since it's instructions, it can't be like the dot data, it has to be the dot text though, right? Or can it be anywhere?
That's a good question. I think instructions cannot go into the dot data section because of the execution inhibit bit. But you know what? Let's give it a try and see if it works. So we intentionally force it into the dot data section. The assembler may not complain about it. Okay, so the problem may not show up until we actually run the program. But we'll see. We'll give it a try. See, assembler does not have a problem with that. The linker may not have a problem with that either because the linker just needs an address. So, yep. And when you actually run the program, it just ran. So there's no execution inhibit when you put code into the data section.
Well, do you know that it actually ran into the data section and just interpreted as nothing you want to deal with and just skipped over it?
Well, let's find out. That's a good point. No, okay. There should be a symbol table.
Not if there's no code.
Hmm?
Is there any code though? I mean, if it's all in the data,
That's a
there's no
good
instructions.
Is it just using, you know, efficiency and
It's assumed
deciding
Same.
that it's not doing anything?
Because
so-
the program has no observable,
Yeah.
you know, output.
Yeah, there's no observable anything. Add one like instruction after it and see, just step into it and see if it does anything.
Or in the subroutine, move something into EAX.
Okay, so this is the actual code of the whole thing. So we have function, it is here, it is definitely in, so underscore start is in dot data. So it does put everything into the right place.
So it decides that you're wrong and it fixes it.
Well, the sub1 can be debugged here too. I just have to figure out how to do it. No symbol table is loaded. It's not being run. If I run it, it says it's exited normally, but I cannot put a breakpoint because it doesn't load the symbol table.
It's not doing anything. There's nothing.
Because it's
Yeah.
not in the text section.
Create a program, add something into the text, just some stupid little thing.
Or just set the main portion of the program in text and just put a dot data in front of the function.
Oh, that's not it. What was the program that we were testing? Sub1. Nope. Oh, we were using the wrong program.
Ah.
Okay. No, it is the right program. Oh, it is the right program. Okay, so well, the easiest thing to do is to put a little dot ASCII here and say A, B, C, D. Just to reinforce the concept that we learned here previously. Move 4 into EAX to request a system service to write something to a file. Move $1 into EBX to specify standard out. Move L, to put a label here. Some text. Into ECX, which is the address of where we are printing from. And in this case, we are just printing 4 characters, so move 4 into EDX. And then invoke the system call, like that. And that should be it. It does print it. Yep, so it ran from the data space. So that means the execution inhibit bit is not set, because otherwise you should not be able to run it from the data section.
Can you print the program in GDB? See if it made any changes.
Sure. So GDB sub1
Yeah.
can't find any code section in symbol file. Okay, that's why it's complaining, because the symbol file is not in the code section.
Interesting.
Everything is in the data section.
Okay.
Yep.
So it didn't optimize anything out that GDB doesn't like that.
Nope, the program assembled and linked just fine. It's just that the symbol table is not at the right place and it couldn't find it. So that's kind of interesting. So the next question is, if I put this stuff into the stack portion, can it still run from the stack? Because that means, a Stack Overflow exploit would work.
The real question is, can you run all your code from .data and allow your code to modify its own code?
I would say it can, because anything in .data can be modified. So you can write self-modifying code if you want to.
Will it need to be recompiled, or should it just work?
What do you mean?
Maybe that was a dumb question.
It does not need to be recompiled. When you compile or when you assemble, you're basically generating the object code before it is self-modifying.
Okay.
But after it self-modifies, there's no easy way for your assembler to understand what it is supposed to be. And that's why self-modifying code a lot of times is used for protecting, copy protection code, so that people cannot just look at the source code and figure out, how to get around the copy protection code. All right. So now getting back to our main business, which is sub1, using the subroutine call. Yep. Go ahead.
Don't most modern processors prohibit that though?
Well, the processor has that bit. The question is, where does it set that bit to? Because that bit, I think, is settable on a per section basis. Because your program has to be loaded into RAM to execute. Okay, it's not running from ROM. It's not your BIOS. Okay, so that means it has to be loaded into RAM in order to run. So the problem is not running from RAM, but running from which portion of RAM and how that portion is designated. If that portion is designated for global variables or the heap or the stack, you should not be able to execute code from that section, because that really is the problem of all the exploits. If that section is designated as code or not text in this case, then the write protection can be turned on for that section, because things should not change in that section, and then you should be able to execute code from that section. So I'm not 100% sure why we can still run it from the .data section, because that should be protected as well, because otherwise you're just going to be inviting all kinds of overflow exploits. How many people already know what a stack overflow or heap overflow or buffer overflow exploit is about?
Get the idea.
Okay, you get the idea. When we talk about the stack, we'll talk about all kinds of problems when you have like a local variable array that only has, let's say, 100 characters. But what happens when you overwrite it with 512 characters, right? And basically the payload of the extra bytes can be executable code, but you have to kind of tweak it in a way so that the return address is returning back to a portion of the stack that contains the payload code. So that really is the tricky part, is how do you know how to hack the return address so it will return to the point where it will start the code that is the actual payload of the malware. So by the time we get there, we might have time to talk about that.
Okay.
And I'm not sure whether I'll be exempt from the DMCA. Nobody cares. Okay, so we're going to single step this entire program. Put a breakpoint at start first, and then we'll single step it. We are on line 5 right now. We call function 1, single step, and now we are on line 13. So if you look at the program on line 13, this is line 12, this is line 13. So we're definitely inside the subroutine function 1. Single step one more time. We're now about to execute a return statement. Where do you think the return should return to? Okay, let me just go ahead and list line 5 and up. Okay, so when we're returning, where should we be returning to?
Line 6.
We should return to line 6, exactly, not line 5. Because if we return to line 5, then it becomes quote unquote an infinite loop, because it would just call the subroutine again. When it returns to the call again. So we should be returning to line 6. Let's go ahead and single step and make sure that that really is what's happening. Okay, so the program does do the right thing, and the rest of the program is not really that interesting, so I'll just continue execution, and it's all done. Okay. In other words, the call instruction is the same thing as calling a subroutine in C. The ret instruction is the same thing as returning from a subroutine, but ret does not specify a return value. There's no such thing as a return value in assembly. Okay, and we'll talk about. But then how do we do things like that? How do we actually return the result of a calculation if everything is done in assembly? So we'll talk about that later.
Just direct memory.
Stored in a register.
You store it into register EAX. It's a convention.
Okay.
It's a convention that is respected by GCC. The code generation. All right. So are there any questions about 12.2, the conceptual behavior of calling and returning? Yep.
If you were in assembly language, if you were to call a function that's not there, or you mistype the name of the function, would the assembler give you an error?
The assembler will not give you an error, the linker will. Because the assembler basically makes an assumption and say, if this symbol is not defined in this file, I'm assuming it is defined by somebody else. So when you're linking, you can link multiple object files into the executable. So the linker is the one that has to double check and make sure all the unresolved references are resolved by the time it's linking. So the linker will complain, but not the assembler. In a C compiler, it's really the same thing. If you separate compilation from linking, when you call a subroutine from C that does not exist, GCC as a compiler should not complain. But when you link using also GCC, the linker will complain about it. Because GCC is kind of like is an integrated command line program. It can do compiling, it can do the linking as well. And that's why sometimes people are not aware that there's a linking process built in when you are going directly from source to executable. Yep.
I have a question. How does a debugger work? Because you use GDB on an executable, but when you view it, you can see all the line numbers.
It's because in the executable, there's a symbol table. The symbol table basically says, this symbolic name maps to this line in this file. Okay, so it might even actually indicate not just the line number, but the actual file location in terms of the byte position. So that's why your GDB can actually say it's basically corresponding an address in your code to a particular line in a text file, in the source file. So by the time you get to a certain location, it can say, oh, do we know where this location maps to in the source file? It looks at the symbol table finds the entry, and then therefore it knows what to display or what to pull from the source file.
And gstabs preserves the symbol table?
Yep, gstabs is the part that makes the symbol table possible. The linker is just copying the symbol table over. Yep. That's a good question. Any other questions before we move on from here? Okay, good question. So to be more precise, the call instruction passes control to a destination specified by the only operand, which is the one on the other side. This operand must be of memory mode. It can be direct, indirect, and so on. The return instruction returns to the instruction immediately following the most recent unreturned call, which is the same behavior as in C and C++. Okay. Yep.
What's the difference between just having like a jump to here and then at the end of that jump to?
Then it won't work when you have multiple calls from different places, because you have an unconditional branch back to a single location, which won't work when you have multiple points to invoke the subroutine.
So it's
Yep.
kind of like jumping to here, but when right before you jump, save where I was before, do the stuff, and then jump back to wherever it was before.
Right. So the magic of call is it can start anywhere. You can put a call from anywhere within your program. When the subroutine is done, it always knows where to go back to. So the next slide will talk about how that is actually implemented. So here's an exercise. We'll skip that. And so we are moving on to how these instructions are actually implemented. But instead of actually talking about the implementation here, let's go back to the program that we already have, and we'll just debug the same program again. But this time, we'll put a breakpoint at start again. But this time, what we'll do is we'll keep track of the stack and the stack pointer. Okay, before and after the call instruction, and then before and after the return instruction, and we'll see how the stack is involved in this process. Okay. So before the call instruction, I'm going to take a look at ESP. It's a particular value, but since this is before we actually have anything to put on the stack, it doesn't really matter whether I display the content on the stack, because it's not something that I put there. Okay, so for now I don't really have to take a look. Single step. Okay, we're in the subroutine right now, and we want to take a look at the stack pointer again. Ooh, the stack pointer changed. And how many bytes, or how is it changed? Is it increased or decreased?
Decreased.
It's decreased. Which instruction from the previous class also decreases the stack pointer. The push instruction or the pop instruction?
Push.
The push instruction. So apparently the call instruction is also doing something that is resembling the push instruction. So if it's pushing something on the stack, we want to find out what is pushed on the stack. So we can use the examine command to do that. We examine one single item as a 4-byte thing. So as a 4-byte thing is a word, and we'll display it as a hexadecimal number. And the location that we are printing from or dumping from is where whatever ESP is pointing to. And it's some really weird hexadecimal number. Okay. So we'll just kind of keep that in mind and then try to figure out what this really represents later on. Okay. So now we're inside the subroutine with single step, and we are about to execute a return statement. Before the return statement, just to make sure the stack pointer is still at this location, and then the content on the stack is still what we had earlier. Okay. So now we single step the return statement. The return instruction has now executed. Now we want to check everything. The stack pointer is back to where it was before the call instruction. But I wonder, what is exactly this number here? This number seems to be it's too weird to be a random number, okay? So what we'll do is we'll just do IR, which displays all the registers, including the instruction pointer, the EIP. So when you look at EIP, which is this one here, that's exactly where we are at this point, okay? In other words, the call instruction just magically push the return address on the stack before it passes control or continues execution at the subroutine. The return instruction is doing exactly the opposite. It's just really going to the stack and use the 4 bytes that are pushed on the stack at that point and pop those 4 bytes and say, I'm going to use these 4 bytes to tell me where to continue execution. And that's basically what happens. So the stack is actually used in a call and a return statement. It's just internal to the instructions. It's just not displayed as push and pop. Are there any questions about this observation? Yep.
What happens if you push stuff on the stack in the function?
What if you
Push stuff on the stack in the function?
Well, that's a good question. If you have push instructions inside a subroutine and you do not pop those, so you have what we call a unbalanced stack, then the return instruction will use whatever the stack pointer is pointing at, the 4 bytes that is pointed to by the stack pointer as the return address. So that may or may not correspond to a location that you wanted to jump back to. Most of the time it is not, but in the rare occasion that it is, then you're in big trouble because the program would not crash right away with the return instruction. It would just return or go to a particular location in your program and continues execution at that point. Okay, so by the time it does crash, it's so far away from the actual return instruction that should have crashed, and that will make debugging that program much harder than just returning to a la la land and just crashes right away.
So you gotta be careful.
So you have to be extremely careful when it comes to assembly language programming. Yep. In fact, we can mess up this program just to illustrate that point. Okay, so let's go ahead and mess up the program. And before we mess it up, I'll just kind of copy this one to sub1 good.s so we can mess up the sub1 without having to worry that, but what was it like before? Okay, so we'll just go to function 1 here. Oops. There we go. And we'll just push, some random stuff on the stack. Okay, let's push, 512 on the stack. Okay. So this is definitely bad because there's no pop corresponding to the push L, so the stack is unbalanced by the time we get to the return statement. So assemble, link, and you know what? The first thing we do is we'll run it without the debugger, and it has a segmentation fault because it's trying to continue execution where there's no instruction from your program. Now, when you GDB the program and you run the same thing, it does give you a segmentation fault, but it tells you where it is right now that is causing the segmentation fault. It tells me that it is at location 200, and it doesn't know what to do at that location. what is 200 in decimal? This is hexadecimal. What is the decimal version? 512. Okay, so whatever I push using the extra push instruction, because the last push, will make the stack pointer point to whatever you just pushed, right? And the return instruction is not very smart. It just says, whatever the stack pointer points to, I will assume that it is the return location. It would just grab those 4 bytes, pop, and increase the stack pointer by 4, and jump to that location. So in this case, since we just pushed 200 in hexadecimal on the stack, it just uses that as the return address, and we are now continuing execution at location 200. Yep.
So if your program had 530 lines in it, it would essentially jump, somewhere in between there, or?
No, it is. This is actually this is the location in memory, so it has nothing to do with the actual number of lines in your code. Yeah, the worst thing is, this number just so happens to map to a valid location in your program. Then we have a much more serious problem. Yep.
So if you wanted to, you could pop right after you got into the function, and then put that into a location in memory, and then right before you return, push it back on.
Yes. In fact, I'll show you something that's even better, even more interesting. Okay. So the question now is, can we implement the call instruction using the instructions that we already know? And can we implement the return instruction using the instructions that we already know? The answer is kind of yes and no. Okay, it's yes to the call, and the return requires one extra thing that we have not talked about. Okay?
Moving the instruction pointer. Moving the instruction pointer. Or
Right,
changing.
or effectively moving something into the EIP register, which is not accessible from software. Okay, so what we'll do is this slide actually talks about that. This actually gives you, most of the correct instructions, except this operand is actually incorrect. So I still need to fix it. But this is really old notes, so it has been wrong for years. Has been wrong for years, and I think that's why I have a correction somewhere. Maybe not. Okay, so let's go ahead and take a look at our sub one. That is, yep, go ahead.
What is the register EIP?
EIP stands for Enhanced Instruction Pointer. It's basically pointing to the next, it's pointing to the address of the next instruction to execute. Yep. All right, so what we can do here is, let me fix this first. So the first thing we want to do is to say, if I do not have the call instruction, can I emulate the effect of the call instruction? Okay. The first thing we have to do is to push the address of the return point, and then we can do a branch to the subroutine that we want to call. Okay. So I'll just kind of outline the template first. So we'll just say push the address of the next instruction. And then the next one is pretty easy. It's just an unconditional branch to the subroutine that we are calling. So that one I can just implement like this. How do I push the address of the instruction following the call? Not the jump itself, but the one it's the no-op instruction basically.
$EIP.
Yep, label it. Yep. First thing is to label the return point, and then we just push. What do we push?
Add brackets.
We actually push $L1. Because L1 itself is, the symbol is representing the address itself. So if you say push L1 without the $sign, then you're pushing the instruction itself on the stack, which doesn't make any sense because you cannot use it for return purposes. But when you say push $L1, it's actually pushing the address of that instruction. So push $L1 is the correct
Couldn't
thing
you
to
have
do.
also done a push $EIP or EIP plus
No,
4?
because EIP is not directly accessible. And plus you want it to be, you want an offset from
That's
it
why
too.
I said EIP plus 4.
You cannot push a register plus something. You have to push the register and then do the math afterwards, or you can do the math and then push the register. But there's no way to access EIP directly, so that option is out.
But there's ways to do it indirectly.
There are ways to indirectly get to the instruction, because all you have to do is to do a call to yourself,
Mhm.
and then instead of using a return, you just pop into a register.
Okay.
All right, so this is done. It is not too difficult. So the next question is, I want to implement return, but if I don't have a return instruction, how do we do it? This one is a little bit more complicated because if I could do it, this is what I want to accomplish. In other words, I'm just using whatever the stack pointer is pointing to as a return address, and I pop that directly into the EIP, so that will change the location of where I will continue execution in this program, right? So that seems to make sense, but that would make things way too simple. So it's not. So we don't have direct access to EIP, and that's why this cannot be done. Well, if this cannot be done, I can still kind of do something like that by popping whatever is on the stack right now into EAX. And then what I need to do now is to say, let's jump to wherever EAX is pointing to. You would think that it has to use this indirect addressing mode, and that's why the notes was wrong. As it turns out, that's the wrong thing to do. It actually needs this particular operand, which we have not talked about. This is basically continuing execution using EAX as the address of where I should go to continue execution. But effectively, okay, if you don't focus on the syntax, but effectively, we are basically saying whatever EAX is the address of where we will continue execution. Is that making any sense? So the second instruction, or the jump instruction, is effectively move L EAX to EIP. But since EIP is not directly accessible, this is the syntax of doing exactly the same thing. Are we still doing okay so far? Okay, so that's call and return. So you would think that, oh, subroutine is covered, all done. Well, as far as doing things strictly in assembly language, yes, we are done with calling and returning. But the question now is, do you want to write your entire program in assembly, or do you want to write your entire program in C? I mean, where's the boundary between this is what I will write in assembly code, and this is what I will write in C and C++ code? Well, sometimes it's really hard to tell. Certain things you can only do in assembly, and certain things you want to do in C because it's a whole lot easier. Okay? What if I tell you that if you play by the same standard as GCC, you can write assembly code that can call C subroutines, or you can write subroutines in assembly language that can be called from C? That would be kind of cool, right? And that's the whole purpose of this class. Remember what I talked about earlier in this class, like in week 1. The purpose of this class is not for you guys to become expert, programmers that can program in assembly language, but to give you the insight of what is happening behind the scenes when you write programs in C and C++. So that's exactly what we'll do, is to understand the standard, of how do we call a subroutine with parameters. Okay, so we'll start with parameters first. Okay, so let's move this out of the way. And I'm going to change the notes here because we're moving on to call frames now. Oh, by the way, there's a little assignment for myself. Implement print hexadecimal, but recursively and without using data constructs. Use EAX as the number to print in hexadecimal. Okay, so let's go ahead and do this because it's kind of an interesting assignment to myself. Okay, it's not your homework assignment, it's my homework assignment. We have about 20 minutes. I think I may be able to do it, including coming up with the pseudocode. No, I do not have everything. I do not have everything prepped before. This is something that I did last year, so now I have to reconstruct everything. I cannot remember the actual solution. Okay, so how do you print a value in hexadecimal using regular C and C++ logic? Let's say you have the shift operator to help you.
You mod it by, so we're printing by 16, so mod the value by 16. And then
If you do the mod method, you'll be printing it in a reverse order.
That's how I start. Well, then I fill the string in from.
You can do that, yep. Okay, so let's go ahead and do it that way, using the mod operation. The mod operation makes it more general, because in this case, because it's a hexadecimal number, you can actually use the left shift operation too, because it will be shifting things the most significant nibble first, so things would actually be in the right order. But we'll go ahead and use the division method to do it. Okay, so we'll do a print hex dot. Let's do it in C first, and then once we get it working in C, we'll do it in assembly, sort of. And we'll start with a non-recursive version of this program. So u in 32.t underscore t n. So you have to pound include. What is the library for all the ins? Cannot remember that. Is it UNI or STDINT? Ah, okay, we'll just look for that. Yeah. Just
Only
keep moving on to
inappropriate.
different resources. If I cannot find it, we'll find the standard in.h. There we go. So I was right to begin with. All right. So we want to print, n in hexadecimal, but using the division method. Let's see how we can do this. I'm going to use a local variable ch to help me remember certain things. So char ch, and we'll start with ch meaning we'll do this in the loop. Okay, so I'll decide what to do with the loop later on. So we'll say ch is n mod 16 in this case. So this program is general purpose enough that you can actually make it work with base 13 if you want to. And then we'll say if ch is less than 10, we'll do one thing. If ch is greater than 10, we'll do some other things. And then we'll go ahead and write to standard out our ch, one single character. And then n itself should be 16. We'll use the quotient of division by 16, with n, so the number that we are actually trying to print is smaller. And this is a big loop. Okay, so we'll say do, and we'll stop when n equals to 0. So when there's nothing to print, we'll just stop. Okay, so we won't print any leading zeros. But you'll see that it's not, it's actually not printing as leading zeros. But we'll see later on. Okay, if ch is less than 10, then we have to say ch plus equal to the ASCII code of 0 itself, because when you're printing, if you print ASCII 5 is a control character. So we want to actually print the ASCII code of the digit 5 by adding the ASCII code of 0 to whatever ch is at this point. Is that making any sense? Converting a value into a printable, ASCII code. So in this case, if ch is greater than or equal to 10, then we have to say ch plus or equal to
A minus 10.
minus 10, because it is off by 10 to begin with. Okay. All right. So this program should work, and to make the compiler happy, we'll go ahead and include unistd.h, which will define the prototype of write itself. And then we'll just go ahead and try this program out. And in this case, I will include argc and no, I probably won't do that. We'll just hard code it.
This may be a dumb question, but is char included in any of those libraries?
Sorry?
Is char included in any of them?
Char is standard.
STD?
Yep. So we'll just say, you know, we'll use a particular pattern that is easy to tell. So A, B, C, D, 1, 2, 3, 4. That's my hexadecimal number to print. And return 0 to make the compiler happy. So I will just compile the code to executable in this case without linking. And it printed out a 4. And that's it. Okay, something is not right. It printed the least significant digit. The loop did not exit. Oh. This always gets me. Because when I teach cisp310, I use repeat until. It would have worked if C had repeat until. But that's actually pretty easy. Do you guys know how to do a repeat until in C? And I think it takes an argument like that. There we go. Now we have a repeat until. I like pound defined, you know. Once again, this will make Professor Fox go like, ooh. Okay, so now the program is correct. Okay, let's see. GCC again. Print. Okay, it prints out everything, but backwards. Okay, right? It's printing out 4, 3, 2, 1, DCBA, and that's because I'm printing out the least significant digit first. Okay, so to make this print everything in the correct order, I got a few options. Okay, if I don't want to change the nature of the loop, I can put it into a buffer first, and then flip everything. You know, swap the first byte with the last, and so on, until everything is swapped, and then I can print the entire buffer out. Or I can turn this into a recursive subroutine, and then I can just decide when to print out the digit, and that will help me reorder everything. Okay, so we'll go ahead and look at this thing again and implement it as a recursive subroutine to fix both problems. Okay, so we'll talk about subroutine as a recursive subroutine, and also fix the printing order thing. Okay.
The other thing you can do is having it create a string as it's going, and you can just add the characters to the beginning of the string.
Oh,
Yes.
And then print a string.
But that will require me to allocate something, and there's always a chance of buffer overrun and stuff like that.
You have to know the length ahead of time.
So what I'll do is I'll do it in a recursive way. Now, if I do it in a recursive way, I don't have a loop anymore. Instead, I have a condition to specify whether I should continue with the recursion or not. Okay, so I'll say if n equals to 0, it is one case, because that for that case I should stop. Okay, there's nothing else to do at this point. Otherwise, we'll do something else. The something else is kind of what we have to do here. So we'll copy line 37 to 47. 37 to line 47. So copy 37 to 47 to here. Okay, so once again, 37 to 47, copy to here. Right. 37 to 47, delete, paste. There you go. Should have used uppercase P to paste before and not paste after. Okay. One thing to change here, this one needs to be changed a little bit, because n divided by 16 is what I would use for the recursive call. So print hex should now be recursive, and do it like this. And when it is 0, we just print 0 out. So in this case, we just have to do a char 0 equals 0, write 1, ampersand 0, 1. Okay, we're done with that one. Okay, what do you think? I think this will work, but it does not change the order of printing, right? So it will still be printing something backwards. Let's double check and make sure that I don't make any silly mistake here. So GCC. All right, I made some silly mistake. Oh, because the new subroutine has the same name as the old subroutine. Fine, we'll just say recursive, print hex. Okay. And we'll go ahead and run the program again, and sure enough, it is still incorrect. 4321 DCBA was the output. So the question now is, how do I fix this program?
It's DCBA 0.
Yeah, there's an extra 0 here. That's basically a leading 0 because I'm waiting until it is 0, but it does print a 0 too. Well, let's go back and change the program. We'll fix the ordering first, okay, and then we'll determine what to do with that leading 0. How do I fix this program now that it is recursive?
Right after.
Right after, exactly. Just switching the write and the recursive call itself will flip the order or reverse the order of printing. Because now instead of doing the recursive call after writing the digit I'm supposed to print, I'm going to say, oh, print all the more significant digits first, and then I'll print my digit. And that will fix the ordering. Okay? It won't fix the 0, but it will fix the ordering. So GCC, print hex again. This time it is printing in the right order, but it has that really annoying, leading 0. Okay, let's go ahead and try to fix that leading 0 problem. Now, to fix the leading 0 problem, one thing you can do is to say, oh, if the number that we want to print is 0, let's not even bother to print anything, right? So you can just kind of comment out this line here. Now, right. This will fix the problem that we have right now because now it's printing A, B, C, D, 1, 2, 3, 4 correctly. But what if you want to print 0 itself? Then it will print nothing because 0 is 0, and so it's not going to print anything.
Actually, as of right now, this program can't print the entirety of any hex that number with 0 halfway through it because it'll stop recurring.
No, it will print anything in between.
I thought you didn't have recursion in the 0 case at all. Oh, do you?
Okay, so let's see whether it will do it or not. It will do it because I'm not checking whether the remainder itself is 0. I'm checking whether n is 0. So n may have a 0 in its hexadecimal representation, but as long as n itself is not 0, it doesn't have a problem. But just to make sure, so it still works. I mean, it's just not taking care of the case when we want to print a single 0. Okay, if the value that we are printing is 0, it's not going to print anything. Okay, so we'll go ahead and test the program again, and sure enough, it doesn't print anything. So what we can do to fix this problem, this is getting back to regular C code debugging and writing programs, we'll keep this one here. It's just that whether we do the recursion or not here determines on whether n divided by 16 is 0 or not. So we'll guard the recursion itself by if n divided by 16 is non-zero, then go ahead and perform the recursive call. That will fix the problem because if n is 0 to begin with, then it would not have gone to this part anyway, so it's not an issue. So let's go ahead and retest the program. It does print 0 by itself.
Will this work? No, never mind.
Okay. Now we have 5 minutes left. I may not have enough time to implement this whole thing in assembly. Okay, so the question now is, if I look at this code, how am I going to do this in assembly? Now, I'm making the assumption right now that I do not have to play by the rules laid down by GCC. So I'm not going to make my program or make this subroutine callable from C or to call any C subroutine from it. So without any consideration of compatibility with C code, can I do something like this in assembly? And I will explain how to use the division instruction, which will get me the quotient and the remainder at the same time. So let's say that's out of the way. Do we have enough instructions to implement this program? And the answer is a definite yes. Okay. But how do we pass pass parameters in this case. I'm just going to go over the general concepts, and then on Thursday, I will finish this entire program. You guys can play with it too. I mean, you can try to implement at least a part of it in assembly. Well, there are many ways to pass parameters. The easiest way is to use registers. So I can just designate a register as my parameter. I can designate EAX, EBX, ECX, or EDX, or any one of those general purpose registers and say that's my N, okay? As long as you play by those rules that you lay down, it's fine. But what about that local variable CH? How do we use CH here? Well, CH is quite useful because CH is used in all of these calculations. You can use another register for that purpose, but if you use another register for that purpose, you kind of have to make sure that you don't mess up, CH, because we are performing the recursion here first, and then we print whatever we calculated before, for this particular invocation. Which instructions or which two instructions can be useful for this kind of thing? I'm putting something push and pop exactly. So before you do the recursion, you push everything that is valuable to you, okay? And then you pass the control to the subroutine, which is also yourself, but it's starting from the beginning. But when it returns back to you, then you say, oh, you know what? I know this subroutine is going to mess up all these registers, but that's okay because I got all of the old values already saved on the stack. So you just have a bunch of pop instructions to pop everything back from the stack so that you can preserve the values of the registers. So theoretically speaking, we do have enough instructions to implement this entire program, save for the division instruction itself. But I think there's a note online already that talks about how to use the diff-L instruction. So combining all the instructions that we already know with the diff-L instruction, we can actually do this already. So on Thursday, what we'll do is, the first thing we'll do is to take a look at this program and actually implement it using a pure assembly way. In other words, it's not going to be C callable, or you can call C subroutines, but we'll kind of address that problem later. So look at this as a brain teaser, and you guys can give it a try and see if you can make it work. I'll see you guys on Thursday.